To the next session of subject engineering maths. We were discussing chapter 4, that is complex variables. Now in this session we start the concept differentiability definition followed by examples and then few basic definitions like analytic function, that is extension of differentiability, continuous function, properties, bilinear transformations, etc. Okay. Now let us see what do you mean by differentiability of a complex valued function. Suppose f of z is a complex valued function. We say that f of z is differentiable. We say that f of z is differentiable if limit h tends to 0, f of z plus h minus f of z by h exists. Whenever this limit is a valid limit, then we say that the function f of z is differentiable. See, here we were discussing differentiability of a function at a general point z. I am not discussing its differentiability, its derivative at a particular point. I am discussing derivative of a complex valued function at a general point. See, whenever this limit is a finite value, that is limit h tends to 0, f of z plus h minus f of z by h. If it exists, then we say that f of z is differentiable, and in this case this limit is denoted by f dash of z. So what is this limit? This is expressed in terms of f dash of z, and this is given by limit h tends to 0, f of z plus h minus f of z divided by h. So this expression is denoted by f dash of z. Now let us see, this is a derivative of f at z. What f dash represents? This is first order derivative of f at z. So f dash of z is denoted by this limit. Limit h tends to 0, f of z plus h minus f of z by h. Let us take an example. Suppose f of z equal to z square. Now what is this f dash of z? This f dash of z equal to limit h tends to 0, f of z plus h minus f of z divided by h. Therefore, this is limit h tends to 0. Here f of z is z square. Therefore, this f of z plus h is z plus h whole square minus f of z is z square divided by h. So, therefore, this is limit h tends to 0. It is in the form a square minus b square. So, the formula is a minus b into a plus b. So, z plus h minus z into z plus h plus z divided by h. This z will be cancelled. So, we get limit h tends to 0, h into 2z plus h divided by h. H and h will cancel. Therefore, replace h by 0, you will get 2z. Therefore, in this case, the derivative of z square is exactly 2z. Just like real variable. If f of x is x square, then its derivative becomes 2x. The same result you are getting even for complex variable also. Okay. So here we got the derivative of f in terms of z only. We didn't find derivative at a general, but at a particular complex value. We got its derivative at a general complex number. Okay. Note these points. Let f of z be any complex valued function. Let f of z be any complex valued function. We say that f of z is differentiable. We say that f of z is differentiable if limit h tends to 0, f of z plus h minus f of z by h exists. If limit h tends to 0, f of z plus h minus f of z by h exists. And this limit is denoted by f dash of z. And this limit is denoted by f dash of z. Example, f of z equal to z square. F of z equal to z square. Therefore, continue all these lines till this moment, f dash of z equal to 2z. Example on differentiability. Suppose if I have f of z equal to z bar. So this z bar is nothing but complex conjugate of z. Let us try to find this f dash of z. So here according to definition, this is limit h tends to 0, f of z plus h minus f of z divided by h. Therefore this is limit h tends to 0, f of z plus h is z plus h whole bar minus f of z means z bar divided by h. Therefore this is limit h tends to 0, z plus h whole bar. So therefore this is z bar plus h bar minus z bar divided by h. Therefore this f dash of z equal to limit h tends to 0. This z bar minus z bar will be cancelled. We get h bar divided by h. So therefore interestingly we got derivative like this, limit h tends to 0, h bar divided by h. Can you guess this value? We can't say, because if h is a real number then h bar becomes h. If 2 is a real number then what is 2 bar? It is 2 only, because it is for a real numbers its complex conjugate will be same part. Then if h is a real number, h bar becomes h. In this case h and h will get cancelled, you will get 1. But this is a complex variable. So in that case h value is gradually tending to 0. So therefore when h is a complex number, h bar will be not equal to h. In that case you won't get any expression. Okay. So therefore this limit does not exist. So this is does not exist. Therefore f dash of z does not exist. Therefore f of z equal to z bar is not differentiable. F of z equal to z bar is not differentiable. Generally people will get doubt at this point. People will write h bar, they will take h bar equal to h. That is true when h is a real number. If h is complex number, h bar will not be equal to h. In that case you cannot cancel out. So limit does not exist. Therefore f of z equal to z bar is not differentiable. Very powerful example, not this. Now we discuss one important point. Suppose we have a complex valued function f of z. Now what is this z? Z is a complex variable. So when you replace z by x plus iy, then this f of z will be in the form u of x comma y plus I into v of x comma y. Now what we are doing is we are replacing a complex variable z by a complex number x plus iy. So simplify the function f of z when z is replaced by x plus iy. Then it will be in the form u of x comma y plus I into v of x comma y. It is a function in the two variables x and y. It is again a function in the two variables x and y. The result is again a complex number. This is real part and this is imaginary part. I am saying that f of z is a complex valued function. That means when you replace z by a complex number x plus iy, the result is a complex number. Therefore what we are doing is z is replaced by x plus iy. In that case the expression becomes u of x comma y plus I into v of x comma y. Let us take an example. Suppose if I have f of z equal to e power z. Now replace z by x plus iy. This is e power x plus iy. So therefore this is e power x into e power iy. Now we have one important result. The result is e power I theta. This is nothing but cos theta plus I sin theta. Very useful result. E power I theta is cos theta plus I sin theta. Therefore in place of theta we have I. This is e power x into, this is cos y plus I into sin y. Therefore this f of z equal to e power x into cos y plus I into e power x into sin y. Now this is my function u of x comma y. So what is u? E power x into cos y. And this function e power x into sin y is v of x comma y. Now I will tell you the importance of this expansion. When you write f of z in the form u of x comma y plus I into v of x comma y, then what are the benefits we get? The most important benefit we get by using this representation is one can easily say the properties of this complex valued function in terms of differentiability, in terms of continuity, in terms of analytic function. Okay. So therefore, when you have f of z representation like this, then these two factors u and v decide whether the function is differentiable at a particular point or not. So based on that, I can go for analytic function. Analyticity of a function is very powerful issue in terms of a contour integral. As I mentioned in the last session, the ultimate task of discussing complex variables is discussing complex integration, that is contour integration. For contour integration, the function must be analytic. To get analytic, the function must be differentiable. But when you go through previous example, f of z equal to z bar, we face some difficulty. We got some confusion when you are finding limit h tends to 0 h bar divided by h. But when you represent f of z in this form, based on some constraints, you can easily say whether the function f of z is differentiable or not. So this representation of f of z makes very powerful sense. Okay. So first note this point. E power I theta equal to cos theta plus I sin theta. E power I theta equal to cos theta plus I sin theta. Next note. Every complex valued function f of z, every complex valued function f of z can be expressed in the form, every complex valued function f of z can be expressed in the form f of z equal to u of x comma y plus I into v of x comma y. Every complex valued function f of z can be expressed in the form f of z equal to u of x comma y plus I into v of x comma y, where u comma v are functions of variables x and y, where u comma v are functions of variables x and y. So you apply this result for this, finally you will get this. Write all these points. Next definition, continuous function. Suppose we have a complex valued function f of z and z naught is a complex number. We say that f of z is continuous at z naught. We say that f of x is continuous at z naught if limit z tends to z naught, f of z exists and this limit must be equal to the functional value. So therefore, limit z tends to z naught, f of z equal to f of z naught. So this definition we had already in case of differential calculus. There we were discussing real variables. Here it is complex variables. There I mentioned very clearly, limit x tends to a, f of x equal to f of a. Limit must exist at that point and that value must be equal to the corresponding functional value. So the same point I was discussing again in case of complex variables. We have a complex valued function f of z. This is my complex number z naught, general complex number. We say that f of z is continuous at this point z naught if limit z tends to z naught, f of z exists. That means the limit of this function must exist at this point z naught. Exist means it's a valid number. It can be real or complex and that number must be equal to functional value. In that case, we say that f of z is continuous at z naught. Let me recall the differential calculus, chapter 3. So when you've gone through polynomial expressions, okay, e power x function, sine function, cos function, all these functions are continuous at all points in the real plane. Similarly, when you look at this in the complex variables, all polynomials constant functions, e power z, sin z and cos z, all these are continuous at all points in the entire complex plane. All polynomials, they are differentiable, they are continuous. Here also constant functions, exponential function, sine function, cos function. In case of real variables, we have discussed even mod x also. when you look at the graph of mod x, it is always continuous. But in this case, the graphical representation of complex variables may not be so simple. So I am not going for graphical representation. Just try to understand the definition. Whatever the definition we had for differential calculus, the same definition we have even in case of complex variables. So whenever limit z tends to z0, f of z exists and it is equal to f of z0, then we say that f of z is continuous at z0. Now when you go through examples, all polynomial expressions in the variable z, for example, when you take polynomial expression like this, suppose z square minus 3z plus 9, this is a polynomial expression, constant function. So for example, 2 plus 3i, this is a complex function, constant function. So e power z, sin z and cos z, this is a constant function. So therefore all these functions are continuous at all points in the entire complex plane. They don't have any drawbacks in terms of derivatives and even in terms of continuity. So all polynomial expressions, constant function, exponential function, sin z, cos z, all these 5 functions are differentiable at all points, even continuous at all points. Okay. So let us write this definition at first. Let f of z be any complex valued function. Let f of z be any complex valued function and z0 be any complex number. And z0 be any complex number. We say that f of z is continuous at z0. We say that f of z is continuous at z0 if limit z tends to z0, f of z exists. If limit z tends to z0, f of z exists and it is equal to f of z0, and it is equal to f of z0, and it is equal to f of z0. Note all polynomials, comma constant functions, comma e power z, comma sin z and cos z, all polynomials, comma constant functions, comma e power z, comma sin z and cos z are continuous at all points, and even differentiable at all points, But regarding modulus of z, we cannot give any assurance about its continuity. So we can discuss modulus of z after discussing one's standard equations. They are Cauchy-Riemann equations. So for the time being, you try to understand these 5 examples: polynomial expressions, constant functions, exponential function, sin z and cos z. Next concept, properties of differentiable functions. Properties of differentiable functions. We have seen the same concept in differential calculus. The same properties will be repeated even here also when a real variable x is replaced by complex variable. Let us see. Suppose I have 2 complex valued functions f of z and g of z. Assume that both the functions are differentiable. Both the functions are differentiable at a point z0. What does it mean? F dash of z0, comma g dash of z0 are finite numbers. They are finite numbers. So this is the meaning. F of z is differentiable at z0. That means when you find the derivative of f of z, and when z is replaced by z0, the quantity is a finite number. It can be real or complex, no issues. The same case with g of z also. So f of z and g of z both are differentiable at a point z0. That means f dash of z0 and g dash of z0 are finite numbers. Now in that case, property 1 is f of z plus g of z is also differentiable at z0. So add f of z and g of z, I will get new complex valued function. Even it has also derivative at the same point z0. So when f of z and g of z are differentiable at z0, then their sum is differentiable. Even their difference is also differentiable at the same point. Similarly, dot is again differentiable. Now replace this minus by dot. F of z dot g of z is also differentiable at the same point. Now when you look at ratio, the result may or may not be true. That is, f of z by g of z may or may not be differentiable at z0. May or may not be differentiable at z0. Since I am saying that it may or may not be differentiable, what does it mean is, in some examples, the ratio is differentiable. In some cases, the result is not differentiable, but I want to say in the negative direction. So one example is required for me. Such examples are called counter examples. Let us see counter example in this case. Suppose f of z equal to 1, g of z equal to z. Now this is a constant function. We know that all constant functions are differentiable at all points. This is a polynomial expression, z power 1. All polynomials are differentiable at all points. In particular, both are differentiable at z0. Here in particular, z0 is taken as 0. When you look at the ratio f of z by z of z, so the result is 1 by z is not differentiable at z0. This is not differentiable at z0 because 1 by z is not defined when z is 0. When the function is not defined at 0, how it is differentiable? The function itself does not exist when z is 0. So ultimately, we cannot say it has derivative at the point 0. Therefore, when you take f of z equal to 1 and g of z equal to z, this is a constant expression, this is a polynomial expression. We know that both the things are differentiable at all points. In particular, both are differentiable at z0 equal to 0. But when you look at the ratio, f of z by g of z is 1 by z, it is not differentiable because the function has no meaning when z is 0. Okay? So note all these points. Let f of z comma g of z, let f of z comma g of z be two functions which are differentiable at a point z0. Be two functions which are differentiable at a point z0. Be two functions which are differentiable at a point z0. Then write all the properties 1, 2, 3. I will tell you point number 4. So for the time being, write property 1, property 2, property 3, sum, difference and product. To property number 4. F of z by z of z may or may not be differentiable at z0. F of z by z of z may or may not be differentiable at z0. Counter example. Consider f of z equal to 1, comma z of z equal to z. Consider f of z equal to 1 and g of z equal to z. Both f of z and g of z, both f of z and g of z are differentiable at z0 equal to 0. Here my z0 is 0. Both f of z and g of z are differentiable at z0 equal to 0. But f of z by z of z equal to 1 by z. But f of z by z of z equal to 1 by z is not differentiable at 0. Is not differentiable at 0. Now, next concept is properties of continuous functions. Properties of continuous functions. The same properties are applicable, but in place of differentiable, you need to write continuous. Suppose we have f of x comma g of x, f of z comma g of z. My variable is z. F of z and g of z both are continuous at a point z naught. Then in that case, their sum is also continuous at the same point. Their sum is also continuous at the same point. Then difference is always continuous at the same point. So dot is always continuous, but f of z by g of z may or may not be continuous at z naught. So the same properties. So the same counter example we can take. F of z equal to 1. We know that all constant functions are continuous at all points. In particular, this is continuous at z naught equal to 0. Now second example is g of z equal to z. So this is a polynomial expression. It is again continuous at 0. But when you look at the ratio f of z by g of z equal to 1 by z, this is not continuous at 0. This is not continuous at 0 because the function itself is not defined when z is 0. Okay. So write the points, properties of continuous functions. So you write the points as it is what we wrote for differentiability, but differentiability is to be replaced by continuous. Then singular point. Suppose we have a complex valued function f of z and z naught is some complex number. We say that z naught is a singular point of f of z if f of z is not differentiable at z naught. If f of z is not differentiable at z naught, then we say that z naught is a singular point of f of z. What does it mean? F of z is not differentiable at z naught. That is, f dash of z naught is not a finite number. That means the derivative of a function at that particular point is not a valid number. In that case, the function has no derivative at z naught, and in that case, this z naught is called a singular point of this function. Let us take an example. Suppose f of z equal to, for example, I can write, for example, z plus 1 by, for example, z square plus 9. Now, when you look at the two functions, the numerator is z plus 1. It's a polynomial expression. All polynomials are differentiable at all points. Therefore, when you take a single polynomial, it has no singular points. It is a second degree polynomial. Only denominator, z square plus 9. Only numerator. It is a ratio of two functions. One is z plus 1 and another is z square plus 9. So, polynomial, no singular points. This is second degree polynomial, no singular points. But when you look at the ratio, the denominator gets 0 when z is plus or minus 3i. So make the denominator equal to 0, z square plus 9 equal to 0. Implies z equal to plus or minus 3i. Therefore, one singular point I call it as z1, this is 3i. Second singular point z2, this is minus 3i. Therefore, these two are singular points of this function. Just make the denominator equal to 0, find its roots. Those become singular points of total rational expression. Okay. So write the definition. Let f of z be any complex valued function. Let f of z be any complex valued function and z naught be any complex number. And z naught be any complex number. We say that z naught is a singular point of f of z. We say that z naught is a singular point of f of z if f of z is not differentiable at z naught. If f of z is not differentiable at z naught, we say that z naught is a singular point of f of z if f of z is not differentiable at z naught. That is, f dash of z naught is not a finite number. F dash of z naught is not a finite number. Write this example. Finally conclude that 3i and minus 3i are singular points of this function f of z. Definition: circle. Very important. The circle concept we use very frequently in contour integration, right? Let us see circle. How to define a circle? Suppose I am starting with one point, for example 2, 3, two-dimensional point. Suppose you maintain all points, or you consider all points which are at a distance of 5 centimeters from this fixed point. So assume that this is one point, the distance between from this point to this point is 5 centimeters. So look at another point. So consider all such points. So all these points are maintaining 5 centimeters distance from this fixed point. Now join all these points. So therefore this is nothing but a circle, and this fixed point we call it as center. And this fixed distance 5 centimeters we call it as radius. Therefore in case of two-dimensional plane, the equation of a circle is x minus a whole square plus y minus b whole square equal to r square. This is the equation of a circle whose center is given by a comma b and radius capital R is given by this small r. Two important factors will decide the equation of a circle. One is center, another is radius. So when you look at this equation of a circle, x minus a whole square plus y minus a whole square, it's a circle having center a comma b and radius equal to small r. But how to define circle? I am starting with a fixed point. For example 2, 3. I am considering 5 centimeters distance. So consider all points which maintain 5 centimeters distance from this fixed point. So there can be infinitely many points. Which are making a distance of 5 centimeters from this fixed point 2, 3. Now join all these points, you will get one representation, geometric representation, that is a closed figure, that we call it as circle. Okay. Now when you look at complex variable, this is equation of a circle in the real plane. When you look at complex plane, the equation of a circle becomes like this: modulus of z minus a equal to r. In this case my center is a comma 0 and radius is small r. This is the equation of a circle in the complex plane. Modulus of z minus a equal to r. What is its center? A comma 0. Radius is smaller. Let us see. Here z is x plus iy. So this implies this is modulus of x minus a plus iy equal to r. This implies modulus of x plus iy, but in place of x we have x minus a. So therefore this is square root of x minus a whole square plus y square equal to r. Apply squaring on both sides. I will get x minus a whole square plus y minus 0 whole square equal to r square. Now when you compare this with this, its center become a comma 0, center becomes, and radius is smaller. So this is the equation of a circle in the complex plane. One example is this. Suppose I have modulus of z minus 2 equal to 3. Now what is the center of this circle? 2, 0 and radius is 3. So this is my number 2 and this is complex variable z. In this case center is 2, 0, radius is 3. This is very, very important. Throughout the contour integration, we use the contour as a circle. Very powerful concept. Write this point. An equation of the form modulus of z minus a equal to r. An equation of the form modulus of z minus a equal to r is called a circle. Having center at a comma 0 and radius smaller. I repeat once again. An equation of the form modulus of z minus a equal to r is called a circle having center at a comma 0 and radius smaller. So write this derivation followed by this example. Next definition, analytic function. Very, very important definition. Suppose we have a complex valued function f of z and z naught is a particular complex number. This is my complex valued function. This is my complex number. We say that f of z is analytic at this point if f of z is differentiable at all points. If f of z is differentiable at all points in some neighborhood of z0. In some neighborhood of z0. So whenever this happens, we say that f of z is analytic at the point z0. This is my complex number z0. We say that f of z is analytic at this point z0 if f of z is differentiable at all points in some neighborhood of z0. In some neighborhood of z0. Okay. So the session seems to be over. I'll repeat this definition in the next session. Okay. Thank you so much.